Okay. Yeah, hello everyone once again. So today is the second lecture of advanced solidity topics. It will be also a bit complex for the first time for the understanding. So yeah, if you have any questions, just stop me and I will answer them. So today I'd like to talk and share how proxies work and how solidity libraries work, what they are, what their use cases are, and also some features. So let's start with the proxies. So what are proxies in the first place? Proxies are special lightweight smart contracts that are usually placed on top of regular contracts that are named implementation contracts. And basically they are needed to provide upgradability and some deployment expenses savings. Proxy contracts work because in EVM there is a special code called delegate call, and proxy is highly used as opcode to work. So basically, proxies are regular contracts with some special logic that allows them to call other contracts in a special way, so that there is an option for the user to change the implementation contract, and if everything is fine, then upgrade happens and this proxy contract can use new implementation contract. Yeah, I hope this is clear. So let's break down how proxies work. So yeah, first of all, proxies are standalone contracts that I have already said, and they use two concepts mainly. The first one is the concept of a fallback function, and the second one is a delegate call. Usually proxies work together with fallback and delegate call, but yeah, there might be other implementations that either don't use fallback functions but use delegate call. Also, it is important that proxies keep their implementation address in a special slot to mitigate storage collisions. What I mean here is that in EVM, every contract has storage, which starts from 0. So the first variable in the storage gets slot 0, and then sequentially slot 1, slot 2, and etc., etc. So if we keep something in a sort of random address, then it is it won't interact with our regular addresses. So it is pretty much safe to store anything there, and there won't be any storage collisions. I'll talk about that later. Then when a user calls a proxy contract, this call with this call data is forwarded to a fallback function, and inside the fallback function there is a delegate call to the implementation contract, and this delegate call basically reads whatever call data is passed to the proxy contract and forwards this call data to implementation contract, where the implementation bytecode is executed. And what is important is that this implementation bytecode is executed not on the implementation storage, but on the proxy storage. So basically, the values of variables stay whatever they are set in the proxy storage, but the bytecode that uses the values of those variables used from the implementation contract. So yeah, let's just quickly understand when fallback and receive functions are called. So I will remind that these are special functions that every contract in Solidity might have. The contract may only have one fallback and one receive like per contract. So you can define 2 fallbacks or 2 receives. But you can add both fallback and receive function in the same contract. So there is a table how to read it. The value here on the left is the data of the transaction, so the data field or the call data length, and on the topmost row we have the order of like what Solidity tries to do. If it fails, then it goes to the next column. If it fails, then to the next column. So when the data is like the data length is more than 0, like basically it is like a function call, just regular function call. First, what Solidity is going to try is to find this function that you are calling. If it finds, then the execution continues. If it doesn't, then it tries to find a special fallback function. If there is no fallback function, then the execution reverts. When data equals 0 or there is no data, so the data field is empty, first what Solidity is going to try is to find a receive function. If there is no receive function, it will try to find a fallback function. If there is no fallback function defined, then the transaction reverse or the call reverse. What is also important is that receive function must be payable. So you can't define a receive function that is non-payable, but payable receive functions may receive no ether. So you can just declare them as payable, but like you are not obligated to send ether to the contract. You can set the value of the transaction to 0, and it will still pass. And the receive function can be virtual. And fallback function, you like may declare it as payable. You may also not declare it as payable. And also fallback function can be virtual. So you could override it in the like child contracts. If the fallback function is not payable, then then the smart contract won't allow it to receive ether with the call. If it is payable, then you can send ether to this function. Basically, you can just define a fallback function, and from this table, you can deduct that the receive function is so the contract will fully work with fallback function only, because regardless of the data length, the fallback is going to be called. And yeah, talking about storage collisions, before we go into the proxy example, let's just understand how storage works in EVM and what proxy contracts do. So first of all, what is storage collision? Storage collision is is when, for example, proxy contract has something stored in slot 0, and also implementation contract accesses or writes to the same slot 0. But because we are using a delegate call, so proxy delegate calls implementation contract, that means that the storage value is going to be used from the proxy contract. But the layout of storage and how this storage is accessed is going to be used from the implementation contract. So if there is something in the proxy contract that was written directly through proxy, for example, like a proxy admin or something like that, and the implementation contract has an access to the slot, then it might like override the data that is kept in this slot, and yeah, might cause some problems. So what is important is what you see like in the contract, the variables that are listed in the global scope of the contract is not the actual storage of the contract. These are just indicators how to access certain storage slots of the contract. But the actual storage is like an abstraction that that you can just like look at and understand what's going on there. And when the delegate call happens, basically the storage, the actual value of storage, like decouples from the storage layout. And this like storage is used from the proxy contract, but the layout in which this storage is accessed is used from the implementation contract. So this is why proxies like keep the address of the implementation in a special slot. So it is like not altered in the implementation. Actually, I noticed here that I have a typo. Yeah, of course, this is not slot 0, but it is slot 1. And here is not slot 0, but slot 2. And yeah, just a typo. Okay, so let's take a look at the proxy example. I will describe how it works. It is rather complex from the first glance, but yeah, I'll do my best to explain. First of all, this is the proxy contract that can be used on top of pretty much any implementation contract. But what is missing in this realization is there is no like upgradability mechanism. So you can implement one, but you will have to write some custom logic on the implementation contract to provide upgradability. Yeah, but okay, we have a constructor here. This accepts the address of the implementation contract. What I do here is that I just use the slot. I've chosen the slot from the EAP 1967. It is the standards of the proxy implementation. So I use this slot, hashed it, and subtracted 1 from it. So this slot is the indicator where I can store the implementation address. So with the assembly, I store implementation address in this slot. And this is the end of the constructor. Then, whenever I call this proxy contract, because there are no functions, there is only one fallback function, which is payable here, but yeah, pretty much doesn't matter. And because there are no functions, the EVM will, EVM will execute the bytecode of this contract, and because there is nothing to call, it will just directly jump to the fallback, if you remember the table on one of the previous slides. So here we enter the fallback function. We have our call data, where we set the so we encoded the function to be called on the implementation contract. So the call data is properly encoded data of some like function on the implementation contract. So here I just once again take the slot. Then I have to extract the actual value from the slot. So I declare the variable here, and with assembly I take the value that is placed under this slot. So here I have the implementation address. Then I am using the low-level delegate call to call the implementation contract and forward the whatever message data I have. Basically, it doesn't matter what I have here. I'm just forwarding it to the implementation contract. If implementation contract reverses, then it reverses. If it doesn't, then yeah, then the execution of the implementation contract is successful, and probably it will update some like storage on our proxy contract. And here is the assembly block that basically checks if execution is not successful. So the OK variable is false or 0. I am reverting. So what I'm doing here is that I'm taking the data pointer because it is the memory variable. The actual variable that I'm accessing here is the pointer where the variable is placed in the memory. I am adding 32 bytes here because bytes are placed in memory in a way that first the length is placed and then the actual contents of bytes are placed. So here I am adding the 32 bytes to go directly to the pointer where the data is placed, and right here. And I'm loading the length of the bytes because the pointer points to the length in memory first. So here is the starting pointer of our memory where to copy the data to return data. And here is the length of the data to copy. And in case of failure, I revert with this return data. And if everything is fine, the argument is the same, but the opcode return is used. Even though fallback function doesn't have like any types to return, and you actually can't declare them, with assembly you can still use return data to return something. And because you're from the front end, you will be using the actual ABI of the implementation contract. The framework that you're using, either Others or Web3, will understand what the function returned and decode it for you. Yeah, so to sum up, what this proxy does is it stores the implementation contract in a special slot. And when the call to the proxy comes, I take the implementation address from the special slot, forward whatever call data is passed, delegate call the implementation contract, and then compare whether the delegate call is successful or not. And depending on that, I either revert or return whatever the delegate call returned. Okay, so what are the benefits of proxy contracts? So the first one is that proxy contracts can upgrade their implementation to overcome the bytecode immutability limitation. So you might remember from one of the previous lectures, I mentioned that bytecode of the smart contract in Ethereum is immutable. So once it is deployed, you are not allowed to change it anyhow. But using proxy contracts can overcome this limitation, because basically what upgrade does is that it doesn't change the bytecode of the existing contract. It deploys new contract with new bytecode, and then proxy is updated so that it points to the new contract with new bytecode. But from the user perspective, this basically means that the bytecode is changed, and it is seamless because storage is not changed. Also, usually proxy contracts are small, like 1 kilobyte of bytecode, not like tens of kilobytes, which makes them less expensive to deploy. Basically, if you have a really huge contract and you're using a factory pattern to deploy those huge contracts, what you can do is not deploy those huge contracts, but instead deploy proxy contracts that will point to this one huge contract. And it will save a lot of money for users who will deploy those contracts. Also, proxy contracts enable the usage of amazing patterns like diamonds and contract dependencies registry. These are like big and complex patterns. I won't explain in detail how they work, but you can Google and check them out yourselves. These are a bit out of scope. And what are the downsides of proxies? The first one is actually the downside of the first. Upside is that because proxies may upgrade their implementations, using them reduces the trust to the protocols that use proxies. So imagine if Uniswap used upgradable contracts. So the trust to Uniswap would reduce significantly, but they not. Their contracts are not upgradable, so you can be sure that what you are executing, what you are calling, is actually like the bytecode of the contract that is going to be executed. But for example, USDC is an upgradable contract, and like they can add whatever they want into USDC and probably break it, or I don't know. So there is like a trust issue with proxy contracts. Also, upgrading contracts is not simple due to storage collisions, and usually contract upgrades bring bugs. What I mean here is that when you're upgrading a contract, it is really important to check that the storage layout of the new implementation is the same or is extended, but not changed. So for example, if you have like two variables, A and B, and in the new implementation, those variables are flipped. So instead of AB, they're listed as BA, then accessing variable B will access the value of variable A. So this is storage collision. And it is really easy to miss them because you have to check inheritance, and you have to check like structs and etc. etc. So there are some tools to check whether the contract is like safely upgradable, and you can use them, for example. Also, the third problem is that clients, for example, you are developing a contract to someone, so this client might think that proxies are a cure for all diseases. However, proxies should only be used for bug fixes and optimization purposes. Rarely, they can be used to upgrade protocols, but you have to consider two issues above. The first one is that you have checked that it is safe to upgrade. And the first one is that you are not like tricking your community. So what clients might think is that if you're using a proxy, then you can deploy like a version 2 of your protocol easily, but it is like not the case. And proxies should be used for bugs, fixes, and some optimization purposes. Yeah, and there are many proxy standards that are used in production code. So here is the list of them. Under transparent proxy, UPS proxy, beacon proxy, minimal proxy or clones, diamond proxy, and legacy inherited storage proxy. Here I have a QR code for you, so you could scan it and read and understand in like more detail what those proxies do and how they work. Yeah, because like describing each pattern will take a lot of time. Yeah, and it is a bit out of scope. But every proxy standard listed here has its own dedicated application in the production code. Okay, so I hope that proxies are understood here. So let's jump into like close, but a bit different section, which are called libraries in Solidity. So let's define what library is. Libraries are contracts that can't have storage, can't have constructors, can have fallback or receive functions, and they also can be inherited from. In Solidity, there are two types of libraries, internal and external libraries. Internal libraries are contracts that are basically inlined into the main contract that uses those libraries, and calling functions of internal libraries basically equivalent to calling internal functions of this contract. And external libraries are external contracts that have to be linked into the main contract, and functions of external libraries are called via delegate calls, which is surprisingly similar to how proxies work. Yeah, let's just quickly define some syntaxes and describe what is using directive. The using keyword is basically a Solidity syntax trigger to indicate that certain variable can be passed first to a library function. So here I define a library, name it library A, which is really similar to how contracts are declared. Then I define a function which I name cast that accepts address, and it is internal. It also returns a uint 256 variable. So in the function body, I just cast the address to uint 256. And this library is internal because there are no external functions and there are no public functions. So basically, internal library can only have internal and private functions. And here I list 4 examples of how to use using directive. The first one is here, which is defined in a global file scope, not in the contract scope, but in the file scope. So this syntaxes will, so compiler will understand that the first variable of type address has to be passed to this function when called. Basically, those 4 examples are sort of equivalent for our case. And here I declare the function cast, which is external. It is defined in the contract B, which is like a regular contract. And here I'm using the function cast directly on the type address. But because I have used the using directive, actually we can use any example of those 4, and this will work. Now, basically, it will forward this variable, the variable what, to the function cast, which is declared in the library A. Yeah, this is the global declaration, which will be available for the whole scope of the file. Then there is a local declaration, which I bind the library to a specific type address. Then there is a local binding for like whatever type there is. So basically, Solidity compiler will try to understand where this function is used, where it is declared. Here it understands that it is in the library A, and it will try to call the library A, passing the what argument as the argument to this function. So here is the binding for every type. Because of course library can have like many functions with many types, and you might want to cast, I don't know, uint 256 back to address. So the type will be uint 256, and Solidity will understand which function you are calling. And also the syntaxes where you explicitly set which function or which type is bound to. Okay. So what are internal libraries? Internal libraries are stateless constructs that can't be deployed on their own. They can only have internal and private functions, and internal libraries are inlined into the main contract during compilation. So here is a simple example. I have a library, internal library with internal function that basically adds to numbers. And here I have a contract example with the external function that also adds to numbers. And because internal library is internal, it has only internal or private functions. Solidity compiler inlines this function into the contract example. And here I'm calling the add function of the library, but this is made via jump, which is the same how the internal function will be called. So basically, I am adding this function to the example contract. This may be useful if this library is used throughout your application. For example, in the older versions of Solidity, before version 8, a very popular internal library was SafeMath. And of course, it is inconvenient to write those save functions in every contract. So you would write it once in internal library and then use it throughout your application. So basically, code reuse. And internal libraries are really cheap. And for example, if there are 5 functions and you're using only 2, the rest 3 functions won't be inlined into your contract. Only the ones that you're using, which is like more convenient than inheritance, for example. But yeah, probably in inheritance optimizer will also clean them up, but I'm not so sure. Then let's jump into external libraries. So external libraries are much more complicated than internal libraries. But why? First of all, external libraries are stateless, standalone contracts that have external functions. External libraries are deployable, and what is important, they have to be linked with the main contract after the compilation. And non-view external functions of this external library can only be delegate called. So there are a lot of verbs here, and what is important here is that external library is basically a smart contract that doesn't have constructor, it can have storage that can be inherited from, etc., etc. And non-view external functions can only be delegate called. So if you deploy this contract, you won't be able to call it directly. You will be able to call view functions from the client side, but there is a catch that is obvious here, because non-view functions can't be called directly, only through delegate call. The message sender in those functions will be the account that called your contract, that's called the library. But if you are calling the view function directly, the message sender might be different here. Or you can also call those view functions from the contract itself. And in that case, the message sender will be also completely different. So the usage of libraries has to be done through the main contract. And probably you shouldn't call it directly in any case. So here is a simple example of an external library. There will be a more complex one. So here is an external library declared because the function that is declared in this library is external. It is rather simple, but when this function and this library is used in the contract, no jump happens here, but a delegate call. Even though the function is view, Solidity still uses a delegate call to call external libraries, not static calls, but delegate calls. And how does external library linking work? So why would you link the library in the first place? So let's just understand how linking works, and I'll then explain why Solidity needs this principle. So when your contract uses an external library, Solidity understands that, and during compilation, it reserves certain byte code where external library is called. The reservation here is the first 17 bytes of cache 256 hash of library full name. What I mean by a library full name, it is the path from the root of your project to the contract, then column, and the name of the library. It uses this string, hashes it, and takes the first 17 bytes. So you can check this hashing yourself by using this line, so contract/example.sol, then column and external library. You can hash it and check that this hash equals. Yeah. Then when the compilation is completed, the linker looks for those reserved places and substitutes those placeholders with the actual library addresses. Here in our example, I have a compilation output that solc provided me. There is a section link references where it lists the external libraries that my contract uses. And also there is an object string, which is basically the init code of the smart contract. And starting from the position 133, we have this strange string, which basically means that this string has to be substituted with the actual address of the library. Solidity compiler will use those placeholders in every place where every external library is used, and it doesn't. So it usually it doesn't work automatically, and you have to do it like sort of yourself. In Remix, this is done automatically by Remix, but if you're using Hardhat, then there are like dedicated functions in others and in Web3 that when called, they will try to find those placeholders and substitute them with actual addresses. But this is not done by the compiler itself. And what do external libraries provide? Why are they useful? So first of all, external libraries work with extended ABI encoding. This is not normal ABI encoding, and using this extended one won't allow you to call contracts from your front end, for example. This extended ABI encoding only works with external libraries. So using this encoding, external libraries can accept storage references. There will be an example, so you will understand what I'm talking about. Also, external libraries are separate contracts. So you can use them to split your bytecode and organize the architecture. Because, for example, you can use external libraries for specific business logic that has to be shared with other contracts, for example. External libraries are stateless. That is why they can be deployed once and used by many other contracts. Say you have developed a special, I don't know, hash function, and this hash function works this way, so it accepts storage references. And you can deploy this contract or external library with this hash function implementation, and then everyone, every Solidity developer, can use this external library in their own project for hashing purposes. And because this library is already deployed, let's say on Ethereum mainnet, developers won't need to deploy those libraries again. They can just reuse because libraries are stateless. And let's take a look at the real-world example of external library usage. Yeah, let's just break down what's going on here. The context is actually not important here. What is important is the capabilities of external libraries. So this one is named governance of chain. It has external function named save of chain results, which accepts 2 arguments of call data and 1 argument of storage reference. Basically, this function will be called from the governance contract that has this variable stored inside of it. And here it will pass the, through the special ABI encoding, through the extended ABI encoding, the storage reference to the basically slot location where this variable is stored. And because this function is called via delegate call, accessing this storage variable will modify the storage of the governance contract, not the library contract. So what happens here is that inside the library contract, I am calling the getSignHash function. It is declared right here, which is public. And through the ABI encoding, I just hash the results hash by appending to it the chain ID and address this. What is cool is that address this will be the address of the governance contract, because the library is called through the delegate call. So address this won't be the address of the library. So I receive the hash and then access this storage reference variable and check that this hash isn't used. If it is, then I am just reverting. If it is not, I am converting this hash to Ethereum send message hash by appending the Ethereum send message in front and hashing once again. And then I'm using the OpenZeppelin ECDSA library to recover the signee of the signature. And then I check that this CNE that I recovered is our trusted verifier. If everything is fine, the execution continues, and once again, using the storage reference variable, I am saving the results cache in the governance contract. And also I am saving that the hash that we calculated is used. So it is not reused anyhow. And what is demonstrated here is basically the certain parts of business logic is taken from the main contract, from the governance contract, and placed into the external library so that governance contract is lightweight, easy to read, easy to navigate, and yeah, pretty much it. External libraries are very, very useful when you are dealing with contracts that want to fit a lot of logic inside. And for example, there is no obvious way to somehow split this logic into different contracts. But one way is to use external libraries for that matter and take certain parts of logic and place into external library. So to so that the main contract won't use as much bytecode. And the second way is to use the diamond proxy pattern, which you can check yourself how it works. But basically, in a nutshell, it is really similar to external libraries, but instead of external libraries, it uses clever techniques to mitigate storage collisions. Yeah, so this is it for today. It was pretty quick, but yeah, you will probably need to watch the lecture once again to understand everything. And also, if you have any questions, leave them in our classroom.
Okay, thank you, Artem. Thank you to all the listeners. It was challenging but interesting. So if there are no more questions, maybe see you later, but wait until tomorrow for the new task. Okay.
Yeah.
So